and welcome back to another chapter of our Physics O-Level lessons. This is our 8th chapter and it's called Electricity. In this chapter, we're going to be learning about electric charges, conductors and insulators, electric fields, current, voltage and resistance. We're going to learn about electrical components, what are those, series and parallel circuits, electrical power, and how we calculate electrical energy. And lastly, what is mains electricity. So here we have the contents and topics of this chapter. We're going to go through them one by one, starting first with static electricity. So, static electricity. This is the definition of static electricity. Static electricity is an imbalance of electric charges within or on the surface of a material or between materials. So the charge remains until it is able to move away by means of an electric current or electrical discharge. So we experience static electricity in a number of different ways in everyday life. Like you may have rubbed a balloon and seen how it will stick to a wall and how your hair becomes puffy after brushing them. So you have observed that static electricity is generated by rubbing. And you have also observed that a charged object may attract an uncharged object. So what happens is that, for example, we notice tiny sparks when we touch a metal door or clothes made of synthetic fibers. So an electrostatic charge builds up on the door and discharges through you when you touch the metal door. So this is charging and discharging taking place when we experience static electricity. So now we have to think systematically about how we investigate this phenomenon. First, how do two charged objects affect one another? So here we have the way of investigating this. A plastic rod is rubbed with a cloth so that both become charged. The cloth and the plastic rod both become charged. Then the rod is hung in a cradle so that it is free to move. So when the cloth is brought close to it, the rod moves towards the cloth. But if a second rod is rubbed in the same way and brought close to the first one, the hanging rod moves away. So now we have seen both attraction and repulsion. And this suggests that there are two types of static electricity. So both rods have been treated in the same way, so we expect them to have the same type of electricity. And the cloth and the rod must have different types. So the two types of static electricity are referred to as positive charge and negative charge. So like charges, by this we mean the two similar charges, for example positive and positive. Like charges like positive and positive will repel from each other, whereas unlike charges will attract each other like positive and negative. They would attract each other whereas like charges repel. So that is why when we bring the second rod close to the first one, it moves away, which means it repels from that rod. Whereas when we bring the cloth close to the first rod, it moves towards the cloth, which means that the rod is attracted to the cloth because the rod may have a negative charge and the cloth would have a positive charge. That in that case, the rod would be attracted to the cloth, whereas the second rod would have the same charge as the first rod because they have been treated in the same way. So then repulsion will occur because both the rods have like charges. So this was attraction and repulsion and the two different types of charges, the positive charge and the negative charge. So now let's look at what electric fields are. So a charged object can affect other objects, both charged and uncharged, without actually touching them. So we say that there is an electric field around a charged object, and any object placed in that field will experience a force on it. So we're going to look at these electric fields in a different topic of this chapter, but for now this is what causes an object to experience a force from a charged object without actually touching them. It is the electric field around this charged object which makes other objects, both charged and uncharged, experience a force. So these were electric fields. We're going to look at the electric field patterns later on, but now we're going to understand friction and charging. So We know that it is the force of friction that causes charging. So when a plastic rod is rubbed on a cloth, friction transfers tiny particles called electrons from one material to another. So electrons are the negatively charged particles found on the outside of the atom, and since they are relatively weakly held, they can be readily pulled away by the force of friction. So an atom has no charge. We say that it is neutral. But when an atom has lost its electron, it becomes positively charged. So if the rod is made of polythene, it is usually the case that electrons are rubbed off the cloth and onto the rod. So since a polythene rod becomes negatively charged when it is rubbed with a silk cloth, we can imagine electrons being rubbed from the cloth onto the rod. So it is difficult to explain why one material pulls electrons from another. The atoms that make up polythene contain positive charges, and these must attract electrons more strongly than those of the silk cloth. That's why when a polythene rod is rubbed with a silk cloth, electrons are transferred from the silk to the polythene. So the silk is left with a positive charge and the polythene becomes of a negative charge because electrons are transferred to it. So this is how friction causes an atom to get charged. So when we rub a cloth or a surface, friction transfers tiny particles called electrons from one material to the other. Now it depends which material transfers the electrons. It depends on the material. Like in the case of the polythene rod and the silk cloth, the electrons are transferred from the silk cloth to the polythene rod. Because the atoms that make up polythene contain positive charges and these must attract electrons more strongly than those of the silk cloth. So that is how friction causes charging. Now we're going to look at charging by induction. So charging by induction. A charged object can attract an uncharged object. For example, rubbing a balloon on your clothes and sticking it to a wall. The wall is an uncharged object which is attracted by a charged one, which is the balloon. Now, how does this happen? We are not rubbing the balloon with the wall, so in that case, friction would cause the charges to build up. But in this case, the balloon is rubbed by our clothes, and when we bring it near to the wall gets attracted to the balloon. So this is basically the charging by induction. Suppose the balloon has a positive charge. It must be attracted to a negative charge in the wall. So the wall itself is neutral, it is uncharged. But its atoms are made up of positively and negatively charged particles scattered throughout. So it's like neutral because it has equal amounts of positive and negative charges. So when the charged balloon is brought close to the wall, its negative charges, which are the electrons, move towards the balloon because they are attracted by it. They may not move very far, but the effect is enough to give the wall a negative charge, which attracts the balloon. So the wall itself is neutral, but when the balloon is brought close, the positive charge move away from the balloon, whereas the negative charge move towards the balloon. And so the wall gets a negative charge. In the same way, if we had brought a negatively charged object close to the wall, then a positive charge would have been induced on the wall. So we say that in this case, we say that a negative charge has been induced on the wall. So this process is known as charging by induction. We can use charging by induction to charge a metal object. So let's look at how we do that. So we start with two objects, the object A and object B. So you can see that object A with a large negative charge and an uncharged metal sphere B on an insulating stand. So object B is neutral, it is uncharged. But object A is negatively charged, it is with a large negative charge, as we can see. So when the metal sphere B is placed near this object A, electrons in the sphere are repelled away. The front of the sphere, which is near A, has an induced positive charge. Now, the sphere is touched either by hand or by a wire connected to earth. and this allows the electrons to escape from the sphere. Because electrons are repelled from the negative charge of this object, they escape to the earth by this wire connected to the earth, or if it is touched. So after this, the connection is removed. Now the sphere B has a positive charge distributed all over it. So finally, sphere B is taken away from object A, and sphere B has a uniformly distributed positive charge all over it. So we have to note that the connection to Earth must be disconnected before B is moved away from A. Otherwise, the electrons would simply run back up to B to neutralize its positive charge. Also, the sphere B and the charged object A never touch. Sphere B gets a charge that is opposite in sign to that of object A. So this is how charging by induction takes place in metals as well, and in different objects. So I hope you have understood charging by induction. It is, as you can see, very interesting and easy to understand. This was negative and positive charges and charging by induction and friction. Now, there is an important thing to understand here. Charging also depends on the materials. So when some materials gain charge, they lose it almost immediately. This is because electrons flow through them or the surrounding material until the balance of negative and positive charge is restored. So these are some type of materials. In the same way, we have different materials which gain charge in different ways. For example, conductors are materials that let electrons pass through them, whereas insulators are materials that hardly conduct at all, and semiconductors are in-between materials. So we're going to look at these conductors, insulators, and semiconductors right now, starting with conductors. Conductors are materials that let electrons pass through them, and metals are the best electrical conductors. This is because some of their electrons are loosely held to their atoms that they can pass easily between them. So these are free electrons, and these free electrons also make metals good thermal conductors. Most non-metals conduct charge poorly or not at all, although carbon is an exception. So those materials which conduct charge poorly or not at all are insulators. Again, insulators are materials that hardly conduct at all. Their electrons are tightly held to the atoms and are not free to move, although they can be transferred by rubbing. Insulators are easy to transfer by rubbing because any electrons that get transferred tend to stay where they are, so it's hard to move them. Insulators can conduct only by friction. So these were insulators, and then we have semiconductors. Semiconductors are in-between materials. By in-between we mean they are poor conductors when cold, but much better conductors when warm. So they are also insulators and conductors, so they are the in-between materials. They become poor conductors when they are cold, but much better conductors when they are warm. So, conductors are materials that let electrons pass through them, and metals are the best electrical conductors. So they contain electrons which are loosely held to their atoms. They are called free electrons, and so they can pass easily in between them. Insulators are materials that hardly conduct at all because their electrons are tightly held to atoms and are not free to move. Semiconductors are the in-between materials. They are poor conductors when cold, but much better conductors when warm. So now we're going to look at the examples of conductors, insulators, and semiconductors. In conductors, we have good conductors and poor conductors. In good conductors, we have metals. Metals, especially silver, copper, aluminium, and carbon. So these are the best conductors. So metals are overall good conductors, but the ones which are best at conducting electricity and thermal energy are silver, copper, aluminium, and carbon. Then we have poor conductors, which are water, human body, and earth. Human body is also included because 70% of the human body is made up of water. Human body is also a poor conductor, but still we can get electrocuted. What happens is when electric charges build up on the cloud when there's a thunderstorm or something, the human body conducts the electric charge, and that is the reason it gets electrocuted. So sometimes Our human body can become good conductors, but they are included in the poor conductor list here. In insulators, we have these. So in insulators, we have plastics and 3 different materials as well. In plastics, we have PVC, polythene, and perspex. Other than plastics, we have glass, rubber, and dry air, which are good insulators. And lastly, we have the semiconductors. We only have 2 different semiconductors, which is silicon and germanium. These are semiconductors. So this was conductors and insulators. So now we're going to look at the unit of charge. So the SI unit of charge is the coulomb. The coulomb is represented by the capital C. So it is equal to the charge on about 6 billion electrons. 1 coulomb is a relatively large quantity of charge, and it is often more convenient to measure charge in microcoulombs. So 1 coulomb is a very large quantity of charge, okay? So we mostly measure charge in microcoulombs. This is how we write microcoulombs. The mu sign with the capital C. So 1 microcoulomb is equal to 10 in the power of minus 6 coulombs, which means 1 millionth of a coulomb. So the charge on a rubbed polythene rod is typically only about 0.005 microcoulombs. So this is even less than 1 microcoulomb. So this is the unit of charge, coulombs. Now we're going to see how we use charge in different devices. And remember, in the following examples, the charge comes from an electricity supply rather than from rubbing. It doesn't come from friction, or it isn't any induced charge. The charge comes from an electricity supply. So we're going to start with our first example, which is the electrostatic precipitator. Electrostatic precipitator is used to clean gases. So as its name implies, it charges particles which are then later removed by being attracted to oppositely charged plates. Well, let's look at it in more detail. Electrostatic precipitators are fitted to the chimneys of some power stations and factories. So they reduce pollution by removing tiny bits of ash from the waste gases. So basically they clean the gas. The waste gases are sent out from the chimneys. So to reduce pollution, the bits of ash from the waste are removed. Now let's look at how an electrostatic precipitator works. So inside the chamber of a precipitator, the ash is charged by wires and then attracted to the metal plates by an opposite charge. So when shaken from the plates, the ash collects in the tray at the bottom. So this is how an electrostatic precipitator is used. It simply charges the particles, the ash particles, by wires, which are then attracted to the metal plate by an opposite charge. Then the ash which is attracted to the metal plates, when they are turned off, when they are shaken, the ash gets collected in a tray at the bottom. So this is the electrostatic precipitator. So the gases pass through the chimneys and these wires charge the ash in these waste gases. When the gases pass through the plates, which have an opposite charge, the ash gets collected on these plates, and the waste gases are more cleaner and they will cause less pollution when they are sent outside because the ash is removed from them. When shaken from the plates, the ash collects in the tray at the bottom. So here you can see the electrostatic precipitator. It's simple. We use this electrostatic precipitator for making sulfuric acid. You might read this in our chemistry chapter in the contact process. We use the electrostatic precipitator to clean air and sulfur dioxide. So there are many uses of an electrostatic precipitator. They are fitted to the chimneys of some power station and factories and are also used to clean not only waste gases but also in some processes it is used to clean other gases which are then used to do a reaction. So these were the electrostatic precipitator. The first example of how we can use charge. The second example of using charge is the photocopier. So this is the process the photocopier goes through. It works using the principle shown in this diagram. Here we have the original document of which we have to make the photocopy. The image of this document is projected onto a positively charged copying plate. When we place the document upside down onto the place and close the photocopier, this is what is happening. The image of the document is projected onto a positively charged copying plate. So wherever light falls onto the plate, the electrical charge leaks away. An image of the original document is projected on the plate. The bright areas lose their charge, but the dark areas keep it. So wherever the light is falling, not the dark areas, which is basically the text in the original document, but the white areas, that's where the light falls onto the plate. So wherever the light falls on the plate, the charge leaks away. So then the dark areas, which are the black areas, the writing, are the only places where the charge is left. Then powdered ink, called a toner, is attracted to the charged areas. Negatively charged black toner. This is a negatively charged. On the plate, they are the positive charge. So the charge is positive. So negatively charged black toner particles are attracted to the remaining positive areas, which are basically the text areas. The white areas are gone. So the toner particles are attracted to the remaining positive areas. After this, a paper is placed over this copying plate and the toner gets transferred to the paper. So the toner is transferred to the paper and heated to make it stick. So that is how we get the photocopy, which is then taken off the copy plate and turned over to reveal the text. So this is the amazing photocopier. This is how this photocopier works. It's pretty interesting, right? Here we have the inside of the machine of the photocopier, the actual machine. This is the original. The flash lamps send light and the light gets reflected off of the original document, and with the reflection we also have a lens in between so that the rays are then reflected from this part, and here is where the real image is formed. Then we have this belt, photoconductor belt. First the plate is cleaned and then it is charged positively. Then it is passed to the real image, and wherever the white areas are, the charge leaks away from that area. Then it is passed to the toner, the negatively charged toner, which gets stick to the positive charge, and then it is passed to the fuser, which basically heats it so that the toner sticks to the paper. So that is why, when we hold the photocopied or printed paper, it is warm because of the fuser, because it is heated so that the toner gets stick to it. So this is the photocopier. I hope you've understood it. The laser printers also use the same idea, except at stage 2. The stage 2 is basically when an image of the original document is projected on the plate. So the bright areas lose their charge but the dark areas keep it. That is the stage 2. The laser printers also use the same idea, except at stage 2, a computer-controlled laser scans the plate strip by strip to create the required image. So these were the different examples that use charges. This is basically the electrostatic charge, the charge which comes from an electricity supply rather than from rubbing. So this is how we use electrostatic charge. You saw many examples. The charge comes from an electricity supply, and we have many uses of these charge in different devices. Okay, so now that we've understood this, we're going to go back to understanding electric field. But this time, we're going to see it in much detail. So this girl here, as you can see, has given herself an electric charge by touching the dome of a Van de Graaff generator. So the force of repulsion between the charges on the girl's head and hairs is strong enough to make her hairs stand up. If electric charges feel a force, then, scientifically speaking, they are in an electric field. So there is an electric field around this dome of the Van de Graaff generator. So now we're going to look at the electric field patterns that positive and negative charges make. So in the diagram, lines with arrows on them are used to represent electric fields. Here we have some examples of electric field patterns. In each case, the arrows show the direction in which the force on a positive charge would act. As light charges repel, the field lines always point away from positive charge and towards negative charge. The force due to the field is a vector. So here we have two opposite charges. The field comes from the positive charge towards the negative charge like this. And if we have both light charges, they would go away from each other. But the arrows always come out from the positive charge and go towards the negative charge. Like here. Here we have bars which produce electricity. So this is the positive terminal and this is the negative terminal. So the electric field pattern is shown as straight lines like this. But the arrows still come from the positive charge towards the negative charge. When a conductor is charged up, the charges repel each other, so they collect on the outside. So in this conductor, as you can see, we only have positive charge and no negative charge. So when this conductor is charged up, the charges repel each other and they collect on the outside of this conductor, like at these points, away from each other, as far away as they can be. So the charges are most concentrated near the sharpest curve. This is where the electric field is strongest and the field lines closest together. So if a sharp spike is put on the dome of Van de Graaff generator, any charge on the dome leaks away from the point. Here the charge is so concentrated that the electric field is strong enough to ionize the air. So ionized air conducts, so the dome loses its charge through the air. Which means that the positive charge will leak away from this sharpest curve because it is so concentrated that the electric field is strong enough to ionize the air, and it leaks away through the air. So ions are electrically charged atoms. Atoms become ions if they lose or gain electrons. If they lose an electron, they would become positively charged. And if they gain an electron, they would become negatively charged. So a stream of ions is a flow of charge. So it is another example of a current. What we mean by ionizing the air is that the molecules in the air gain or lose electrons to the charge which the dome loses. So the air becomes ionized, either positively charged or negatively charged. So most of the molecules in air are uncharged, but not all. Flames, air movements, and natural radiation from space or rocks can all remove electrons from molecules in air so that ions are formed. With no ions in it, air is a good electrical insulator, but with ions present, it has charges that are free to move, so the air becomes a conductor. So, because air also has charged atoms, they get attracted to the electric field of this charge inside the conductor. A negative charge from the conductor is induced in the air. In the same way, in a thunderstorm, the concentrations of different ions may be so great that a very high current may flow through the air, causing a flash of lightning. Like here we can see many examples. A lightning may occur from one cloud to another cloud, or within cloud, or from cloud to the ground, or from cloud to the air. Because air is also a conductor, it also has ions. So if this cloud has positive charge over here and this cloud has negative charge, lightning would flow from this one to here, like this, because opposite charges attract each other. In the same way, opposite charges in the cloud and the ground cause lightning to occur. And lightning also occurs within the cloud if the cloud contains positive and negative charges, both. So this is how lightning occurs in thunderstorms. Because of charges and ions, a very high current flows through the air, causing a flash of lightning. So now that we've understood static electricity, charges, ions, electric field patterns, the use of electrostatic charge in many different devices like the photocopier, semiconductors, insulators, and conductors, charging by induction and charging by friction, what is attraction repulsion between charges. So we can now move ahead onto understanding current in a simple circuit. So, the current in a simple circuit. An electric cell can make electrons move, but only if there is a conductor connecting its two terminals. Then, chemical reactions inside the cell push the electrons from the negative terminal round to the positive terminal. So the cell here in this example is being used to light a lamp. As electrons flow through the lamp, they make a filament heat up so that it glows. The conducting path through the lamp, wires, switch, and battery is called a circuit. This is a complete circuit. There must be a complete circuit for the electrons to flow. Turning the switch off breaks the circuit like this, and the current stops flowing. When the switch is turned on, the wire gets connected to this part and the circuit is complete. So the electric current flows in a complete circuit, making the filament heat up so that it glows. So the circuit can be drawn using symbols, circuit symbols. These are the circuit symbols. There are many circuit symbols which have different meanings, but the main ones we use in a simple circuit are the switch, the lamp, and the battery. The switch is like this. If it is turned off, the switch is open. And if the switch is turned on, it is called closed, like this. We have many other circuit symbols as well, like the thermistor. We're going to see what this is later. The cell. This is a cell, a battery. The battery is made up of many cells. So a cell would be like this and a battery would be like this. Then we have the voltmeter and the ammeter. The ammeter measures current, whereas the voltmeter measures the current difference. We're going to see this later in the other topics of this chapter. We have diode, which looks like this. Inductor, we're going to see this later as well. LDR, it stands for light dependent resistor. Buzzer, and the plain resistor. Also have the fuse, the ground. This basically shows the connection to the ground, like in the starting we saw here. This sphere was connected to the ground, so we use the symbol to represent connections to the ground. So these are the different circuit symbols. Now we're going to see how we can measure current. As I said, we have different devices like the ammeter and the voltmeter to measure current. We're going to see how we do this. So, a flow of charge is called an electric current, like positive charge and negative charge. Like in a cell, we have two terminals, the negative and the positive, and the charges flow from the positive terminal towards the negative terminal. So, a flow of charge is called an electric current. The higher the current, the greater the flow of charge. So the SI unit of a current is the ampere. This ampere is represented by a capital A. And about 6 billion electrons flowing around a circuit every second would give a current of 1 ampere. However, the ampere is not defined this way. Currents of about an ampere or so can be measured by connecting an ammeter into the circuit. So here we got the ammeter. This is the ammeter. For smaller currents, a milliammeter is used. So the unit in this case is a milliampere. When we use a milliampere is the unit in this case. So 1000 milliampere is equal to 1 ampere. So here we have some typical current values. Here the values are written in amperes. So 0.2 amperes is the current in a small torch lamp. 4 amperes is the current in a car headlight lamp, because the car headlights needs more current than a small torch. And about 10 amperes of current in an electric kettle element. So putting ammeters into a circuit has almost no effect on the current. As far as the circuit is concerned, the meters act just like pieces of connecting wire. So they do not affect the current in a circuit. So here we have the circuit which has 2 ammeters in it. These are the ammeters. Any electrons leaving the battery must flow through both of the ammeters, so both of the ammeters give the same reading, because the current is the same at all points in a simple circuit. So this is what we learned here. The current is always same at all points in a simple circuit. But in some complex circuits, the ones which contain resistors, their current may differ at some points. But in a simple circuit, like this one, the current is the same at all points. So this is the ammeter and how we measure the current. The ammeter basically gives us values of the current, like 0.2 ampere, 4 ampere, 10 ampere, or sometimes in milliamps if the device current is very small. So now let's look at the link between charge and current. So there is a link between charge and current. So if charge flows at this rate, then the current would be this. So the charge flows at 1 coulomb per second, the current would be 1 ampere. If the charge is 2 coulombs per second, then the current is 2 amperes. So this link can also be expressed by an equation. This is a much better way to do so. Current is equal to charge upon time. And in symbols, we write it as I is equal to Q upon T. Q and I are capital, whereas T of time is small. For example, if a charge of 6 coulombs is delivered in 3 seconds, the current is 2 amperes. We basically divided 6 coulombs into 3 and what we get is 2. So the current is equal to 2 amperes. So if the charge flows at 1 coulomb per second, the current is 1 ampere. So this is the equation we use to express this link. Current is equal to charge upon time. The charge gets divided by time and we get the current. So we can also rearrange this equation to get other values like the charge and the time. And how do we rearrange the equation? You know what I'm saying. We use the rearranging triangle, the one I have been using throughout this series of videos. How can we make this triangle this time? I want you guys to understand and tell me how the triangle would look like using this equation, where all of these values would be placed. Remember, one value is on the top and two values are multiplying together at the bottom, dividing the top value. So which values are going to be at the top and which are going to be at the bottom, multiplying together. So it's simple. We see the value which is on the top right now here, which is, as you can see, the charge. The charge is getting divided by time. So if the charge is at the top, it won't come down if we have to rearrange it. The charge would stay at the top and the current would go down with time. So what we get, current multiplying by time and dividing the charge. So then we have the triangle. Using this triangle and this placement of these values, we can find any of the values. We can rearrange the equation in the same way. So say for example, I would want time. I would simply hide the time under my finger and what I will get is charge dividing by current. So then we would have to divide charge by current. So you can see that the charge remains at top. It won't come down. If any value is given like this, like two values are divided to give another value, that value which is at the top will remain at the top and the two other values would go at the bottom. But if we are given an equation in which two values are being multiplied to give another value, then the multiplying values would be at the bottom and the value which they both are giving would be at the top. So that is how we make the rearranging triangle in order to rearrange an equation. In the same way, if we would want to find current, we would simply hide the current under our finger and what we get is charge divided by time. And if we want charge, we will simply get current multiplying by time. So this is how we rearrange this equation to get any of these values. I think that this rearranging triangle can be very helpful in remembering how we can rearrange the equation in whichever form it is given. So now that we've understood charge and current and this equation, the link between charge and current, it's better to write down this equation so that we remember it. We use this equation in different questions related to charge and current. So now we're going to move ahead onto understanding current direction. So some circuit diagrams have arrowheads marked on them. These show the conventional current direction. The conventional current direction is the direction from positive terminal to the negative terminal around the circuit. The ones I was talking about before when we were understanding electric fields. But that is the direction of the conventional currents. If we talk about electrons only, electrons actually flow the other way. Because they are negatively charged, they are repelled by the negative charge. So are pushed out of the negative terminal of the battery. So here is what conventional current looks like and then electron flow looks like. The conventional current comes from the positive terminal and goes towards the negative terminal. But because electrons are negatively charged, they get repelled from the negative terminal and go towards the positive terminal. So the conventional current direction is equal to the direction of transfer of positive charge. Mathematically, a transfer of positive charge is the same as a transfer of negative charge in the opposite direction. The rate at which both the charges flow is the same, but the only difference is that the direction is opposite to each other. So now that we've understood the current direction and the electron direction, we're going to move ahead onto now understanding potential difference across a cell. So, a cell normally has a voltage marked on it. The higher this voltage would be, the more work is done in pushing out each coulomb. In other words, the more energy per coulomb is transferred by the electrons to the lamp. So we're talking about a simple circuit here, the one which supplies current to the lamp to make it light up. So the higher the voltage of a cell would be, the more work would be done in pushing out each coulomb. So the more energy per coulomb would be transferred by the electrons to the lamp. So the scientific name for voltage is potential difference, also known as P dot D dot, PD. It can be measured by connecting a voltmeter across the terminals. So the SI unit of potential difference is the volt. In symbols, it is written as capital V. So potential difference is basically voltage, a scientific name for voltage. Voltage is basically another name for the work done in pushing out each coulomb, and we also call voltage potential difference. So potential difference, charge, and work done are linked by this equation. V is equal to W upon Q. V represents potential difference, W represents work done, and Q represents the charge. So if we divide work done with charge, we will get the potential difference. In the same way, we can rearrange the equation using the rearranging triangle. So for example, if the potential difference across the cell is 1.5 volts, then 1.5 joules of work is done in pushing out 1 coulomb of charge. 3 joules of work is done in pushing out 2 coulombs of charge, and so on. So this is how the potential difference is found using charge and work done. So how much work is done in pushing out the amount of charge, that will be equal to the potential difference. So the potential difference across the cell is highest when it isn't connected in a circuit. This maximum potential difference is called the electromotive force, also written as EMF, of the cell. This is the electromotive force of the cell, which is basically the maximum potential difference a cell has. And this potential difference across the cell is highest when it isn't connected in a circuit. So when the cell is supplying a current, the potential difference across it drops because the cell heats up and energy is also wasted. For example, a car battery labeled 12 volt might only produce 9 volts when being used to turn a starter motor, because some energy is also wasted in the form of thermal energy. So in other words, 12 volts is the electromotive force of the battery and 9 volts is the actual potential difference of the cell. So now this was potential difference, voltage. How we can measure the potential difference using this equation, using charge and work done. Potential difference is basically another name for the work done in pushing out each coulomb of charge. So when we divide work done with charge, we will get the potential difference. Potential difference is also called voltage of a cell. And the electromotive force of a cell is the maximum potential difference it has. And this is only when the cell isn't connected in a circuit. Because when the cell is supplying current, the potential difference across it drops because the cell heats up and energy is wasted as well in the form of heat, in the form of thermal energy. The total energy a car battery or any battery can supply is the electromotive force of it. This is the maximum voltage it can supply. So this is the electromotive force. So to produce a higher potential difference, several cells can be connected in series, which is in line. like this. This is called the cells in series. So the word battery really means a collection of joined cells, although it is commonly used for a single cell as well. So in symbols, the cells are shown like this. So to have a higher potential difference, a higher voltage in a circuit, several cells are connected in series like this. And each cell supplies 9 volts of potential difference, 9 volts of voltage. So in total, all these cells provide 36 volts in a circuit. Otherwise, a single cell would only provide 9 volts. Whereas this group of cells, we can also call this a battery. These group of cells supply much more voltage than a single one. So this is cells in series. In this circuit, as you can see, the electrons flow through 2 lamps. These are the 2 lamps. So some energy is transferred to the first lamp and the rest to the second. If the connecting wires are thick enough not to heat up, no energy is wasted in the wires. Otherwise, some of the energy also gets wasted as thermal energy from the wires. So like the battery, each lamp has a potential difference across it. If a lamp has a potential difference of 1 volt across it, then 1 joule of work is done in pushing each coulomb of charge through it. So potential difference of 1 volt means that it requires 1 volt to make it work. It requires 1 volt of current to make it work. So that means then 1 joule of work is done in pushing each coulomb of charge through it. As a result, 1 joule of energy is transferred to it. The same thing I was talking about. So the readings here illustrate a principle which applies in any circuit. Moving round a circuit from one battery terminal to the other, the sum of the potential differences across the components is equal to the potential difference across the battery. If the lamps require more energy than the battery is providing, they would not work. And if they require less energy than the battery is providing, then again they will not work. The circuit would not work. So the sum of potential differences across the components, these lamps, is equal to the potential difference across the battery. In simple words, the battery is providing the exact amount of current these lamps need. So if a lamp or any other component has a potential difference of 1 volt across it, then 1 joule of work is done in pushing each coulomb of charge through it. Basically, the electromotive force of a cell is the work done per unit of charge by the cell in driving charge around a complete circuit, including the cell itself. The potential difference across a component is the work done per unit of charge in driving charge through the component. This was potential differences around a circuit. The principle which applies in any circuit, that moving round a circuit from one battery terminal to the other, the sum of the potential differences across the components is equal to the potential difference across the battery. The battery is basically cells in series. This is what a battery is. So when several cells are connected in series, in line, they produce a higher potential difference compared to a single cell. So here we have the definitions of some of the things we learned here: the electromotive force and the potential difference. The electromotive force of a cell is the work done per unit of charge by the cell in driving the charge around a complete circuit, including the cell itself. The potential difference across a component is the work done per unit of charge in driving charge through the component. So here we saw that the potential difference of this lamp is 2 volts and this lamp is 1 volt. So the potential difference across the battery is 3 volts. So it is equal to the sum of these two voltages. So now let's move ahead on to understanding what resistance is. So to make a current flow in a conductor, there must be a potential difference across it. There must be a voltage across it. So copper connecting wire is a good conductor and a current passes through it easily. However, a similar piece of nichrome wire has more resistance than the copper wire. So what is this resistance? Resistance is calculated using this equation. The SI unit of resistance is the ohm, and we use the Greek letter omega to represent it. So the equation to calculate resistance is resistance equal to potential difference across conductor divided by current through conductor. So for example, if a potential difference of 6 volt is needed to make a current of 3 ampere flow in a wire, then when we divide 6 by 3, we would get a 2 ohm resistance. So this is what resistance is. With a lower resistance, a lower potential difference would be needed to give the same current. So even copper connecting wire has some resistance. However, it is normally so low that only a very small potential difference is needed to make a current flow in it. And this can be neglected in calculations. So there are many different factors on which the resistance of a conductor depends. The resistance is basically something that resists the current through a conductor. So the higher the resistance would be, the less the current would flow in a wire to produce. The more a current would flow in the wire to produce a specific potential difference across this conductor. The less the resistance would be, the less current would be needed to provide this specific potential difference across the conductor. Here we have the factors that I was talking about the resistance of conductor depends on. Firstly, the length. Doubling the length of a wire doubles its resistance. So the longer the wire would be in which the current is flowing, the double its resistance, the more its resistance would be. Secondly, the cross-sectional area. Having the end-on area of a wire doubles its resistance. So a thin wire has more resistance than a thick one. So the more thick the wire would be, the less resistance it will have. Thirdly, the material. So a nichrome wire has more resistance than a copper wire of the same size, because the material of nichrome is different from copper. Lastly, the fourth point is temperature. So for metal conductors, resistance increases with temperature. For semiconductors, it decreases with temperature. So temperature, material, cross-sectional area, and length of the wire are the factors on which the resistance of a conductor depends. So the more the length of the wire would be, the more its resistance would be. The less the cross-sectional area of a wire would be, the more its resistance would be. The resistance would also depend on the material of a wire. For metal conductors, the resistance would increase if the temperature would increase, but for semiconductors, the resistance would decrease with the temperature. When electrons collide with atoms as they pass through a conductor, the electrons lose energy and the atoms gain energy. Thus, the particles move faster and heat up. So, faster vibrations mean a higher temperature. This principle is used in heating elements and also in light bulbs with filaments. So the more the current would pass through a conductor, the more the electrons would lose energy and the more the wire would heat up, which means that there would be a higher resistance. As temperature increases, the resistance also increases. So this was one link between heating effect and resistance. Now we're going to look at the different resistance components. So there are many of the resistance components. Here we have a few. So now we're going to look at the resistance components, starting with resistors. So this is what a resistor looks like. Resistors are specially made to provide resistance. So in simple circuits, they reduce the current. In more complicated circuits, such as those in radios, TVs, and computers, they keep currents and potential differences at the levels needed for other components to work properly. Resistors are specially made to provide resistance. So the resistance already is there in many different conductors. There is always some resistance in a conductor, but we also have resistance components which provide resistance in circuits. So in simple circuits, they reduce the current, but in more complicated circuits, such as those in radios, TVs, and computers, they keep currents and potential differences at the levels needed for other components to work properly. So in more complicated circuits, they keep the levels of potential differences needed for other components to work properly.
So these are what resistors are. They look like this. They have some stripes on them. Each stripe represents some value. The second resistance component is the variable resistor. We also call them rheostats. This is what they look like. So rheostats are used for varying current, variable resistors as their name implies. They may be used to control the brightness of a lamp and are also used in hi-fi equipment. Rotary variable resistors are used as volume controls. Like you can see here, we have a circular variable resistor. So they're used as volume controls. They basically vary the current. Whereas resistors, they have a special value of their own. Their resistance cannot be varied. It will remain the same. Whereas variable resistors, they are used for varying current. Like in volume controls, we can make the volume higher or lower using these resistors. We turn the knob of these resistors, which is basically this part here, as you can see in this image, and when we increase the volume, the resistance of this resistor decreases, and when we decrease the volume, the resistance of the resistor increases. So these are variable resistors. We have rotary variable resistors and simple variable resistors as well. The next resistance component is the thermistor. The thermistor have a high resistance when cold, but a much lower resistance when hot. So they contain semiconductor materials. Some electrical thermometers use a thermistor to detect temperature change, like in alarms, like fire alarms. When the temperature rises too much, the thermistor's resistance becomes less and the current flows more. So that is how an alarm turns on, because of the increased current. So these were thermistors. We use semiconductor materials in thermistors because they're poor conductors when cold but much better conductors when warm. So this is the reason we use such materials, semiconductor materials, in thermistors. So after thermistors, we have light-dependent resistors. As their name implies, they have a high resistance in the dark but a low resistance in the light. So they can be used in electronic circuits which switch lights on and off automatically. So light-dependent resistors are used to switch lights on and off automatically. Now we're going to look at the last but not the least resistant component, the diodes. So the diodes are used to allow current to flow in one direction only. Diodes have extremely high resistance in one direction but a low resistance in the other. So in effect, they allow current to flow in one direction only. They are used in electronic circuits. They make the current flow in one direction. And that is basically the direction where the resistance is low than the other direction where the resistance is high. So the current flows in the direction where there is a low resistance of the diode. So these were the resistance components. Here we have the resistance components with their circuit symbols. The thermistor has this circuit symbol. This is the resistor symbol. The diode is represented with an arrow. The direction of this diode can be reversed. If the current is in this direction, then the arrow would point in this direction. This is the variable resistor. It has an arrow in between, and the light-dependent resistor. So these were the resistance components. Each one has a different use in different scenarios. So I hope you have understood resistance. This was the equation of resistance, potential difference divided by current, and we get the resistance. The SI unit of resistance is the ohm. So now that we've understood resistance, we are going to move ahead onto understanding the link between current, voltage, and resistance. So here we have the VIR equation. This is the resistance equation. We have written it using symbols here, where R represents resistance, V potential difference, and I current. So the resistance equation can be written using symbols, and this is the triangle we use to rearrange the equation. Now remember, don't confuse the V with the V we use for volt. This V is italic, the one which represents potential difference. The V we use to represent voltage or the one we use to represent volt, which is not italic. This one is italic. So now we're going to use this equation in this example. So a 12 ohm resistor has a potential difference of 6 volt across it. What is the current in the resistor? So we're given the resistance and the potential difference of the resistor, and now it's asking us to give the current. So we're going to simply use this equation, R is equal to V upon I, and answer this question. In this case, V is equal to 6 volt, R is equal to 12 ohm, and I is to be found. So we rearrange the equation using this triangle. We want to find the I, so we hide the I, and what we get is V dividing by R. So we divide V by R, that is, we divide 6 by 12, and we get 0.5. The current is 0.5 amperes. It's just as simple as it looks like if we remember this equation. So this is how we use this equation to find out different values like the current, the potential difference, and the resistance. So now let's see how current varies with potential difference for a metal conductor. This experiment can be used to investigate how the current in a conductor depends on the potential difference across it. So the conductor in this case is the coiled up length of nichrome wire. This is the nichrome wire. This nichrome wire is kept at a steady temperature by immersing it in a large amount of water. So the potential difference across the nichrome can be varied by adjusting the variable resistor here. So we have a circuit. In this circuit, we have a nichrome wire which is dipped into water, a lot of water, and heat is being given on this water, and the temperature is kept steady. The potential difference can be adjusted of the nichrome wire using this variable resistor, and we have a voltmeter and ammeter to check the current. We have an ammeter to see the current, and we have a voltmeter to measure the potential difference. So typical results are shown in the table here. This experiment is also a method of measuring resistance. When the potential difference was 1 volt, the current was 0.2 amperes. And so when we divide the two values, we get 5 ohms of resistance. Then when the potential difference increased to 2 volts, the current increased to 0.4 amperes, and the resistance remained the same, 5 ohms. Then the potential difference increased to 3 volts, the current to 0.6 amperes, but the resistance still remained the same, 5.0 ohms. So as you can see, as the potential difference increases, the current also increases, but the resistance remains the same. Of course, if we divide 3 by 6, 3 by 0.6, we will get 5. This is how the resistance is checked. These results can also be shown using a graph. So the potential difference and the current are both steady, so the resistance is also the same. This is the graph. So this is how the current varies with potential difference for a metal conductor. So in this experiment, the results have these features. A graph of current against potential difference is a straight line through the origin. So if the potential difference doubles, the current also doubles, and so on. And the potential difference divided by current always has the same value, which is 5 ohms in the case. So mathematically, these can be summed up as the current is proportional to the potential difference. And this is known as the Ohm's law, after George Ohm, the 19th century scientist who first investigated the electrical properties of wires. From these results, the experiment, we can see that if the potential difference doubles, the current also doubles. And the resistance remains the same. So from this we can see that the current is proportional to the potential difference. It is always proportional to the potential difference. This is known as Ohm's law. So this is Ohm's law. A metal conductor has a constant resistance, provided its temperature is constant. This is not always the case with other types of conductors because their temperature may vary. But in this case, we kept the temperature constant and so the metal conductor has a constant resistance as well. So here we have two more examples of current potential difference graphs, and in both of these examples the resistance varies depending on the potential difference. So here we have a semiconductor diode and a tungsten filament. So in this graph, the 0 is at the center of the line, and minus values are written over here and plus values are written over here, whereas all the other graphs start from the 0 over here and there are no minus values. So in the case of diode, the negative part of the graph is for readings obtained when the potential difference is reversed. That is, when the diode is connected into the test circuit in the opposite way round. So that is how it is done. So as you can see, the current in this graph is not proportional to the potential difference. And if the potential difference is reversed, the current is almost zero. In effect, the diode blocks the current in the reverse direction. So its resistance is greater in one direction and weaker in one direction. So this is the semiconductor diode. In the tungsten filament you can see here, this has a 0 over here, no negative values here. As the current increases in this diagram, the temperature rises and the resistance goes up. So the current again is not proportional to the potential difference, because firstly the temperature is varying and the resistance is also varying. What Ohm's law says is that the current is proportional to the potential difference and the resistance would remain the same, like in this case. This perfectly represents Ohm's law, because the potential difference and current are proportional to each other, so the resistance is the same. This is not always the case with other different conductors, like here, the semiconductor diode and the tungsten filament, because temperature varies in these. So this is how temperature varies the resistance of a conductor. Now we can also see how the resistance also depends on the length and area of a wire. So the copper wires, these two copper wires, have the same cross-sectional area and temperature, but B is twice as long as the A wire. So as a result, it has twice the resistance of A. Provided other factors do not change, resistance is directly proportional to length. So if the length will increase, the resistance would also increase. If the length decreases, the resistance decreases. This symbol, as you can see here, represents directly proportional. Now in these copper wires, the wires have the same length and temperature, but B is twice the cross-sectional area of A. And so as a result, it has half the resistance of B. So provided other factors do not change, resistance is inversely proportional to area. This is how we write the inversely proportional. We say directly proportional to 1 divided by area, which means that it is inversely proportional to area. So if the area increases, the resistance decreases, and if the area decreases, the resistance increases. This is what we mean by inversely proportional. So B has half the resistance of A. So these proportionalities are true for other types of wires, although the resistance will differ. So for example, nichrome has much more resistance than copper of the same length, cross-sectional area and temperature. So it already is different. Its resistance is already more than copper, even if these factors are kept the same of both the wires. The resistance is still more than copper because it also depends on the material. So for any given conducting material at constant temperature, resistance is directly proportional to length divided by area. In simple words, just to make it simple and not confuse this, resistance is directly proportional to length and inversely proportional to area. So by directly proportional we mean if length increases, the resistance will also increase, and if the length decreases, the resistance will also decrease. But it is inversely proportional with area, which means that if area increases, the resistance decreases, and if the area decreases, the resistance would increase. So this is the link between the resistance and the length and area of a wire. Now that we've understood so much about this stuff, we have understood resistance pretty well, the different equations of resistance, We're going to do some proportionality problems here. Questions, in other words. So, the proportionality linking resistance, length, and area can be converted into an equation like this. So, R stands for resistance, P is the constant for the material at a particular temperature. P is called the resistivity of the material. So, P multiplied by L upon A. L is the length and A is the area. So, if we rearrange this equation, we can see that P is equal to R into A upon L. So, if we multiply resistance with area and then divide the value with the length, we can find the resistivity of the material of the wire is made of. So this is another equation. It's a very good one because I was saying already that the resistance also depends on the material the conductor is made of. So nichrome has much more resistance than copper because their materials is different. So how can we calculate the resistivity of a material? This is how we do so. We multiply resistance by the area of the wire and then divide it by the length of the wire. So if we do this for both copper and nichrome, which have the same length and area, but because the resistance is different, we can find out that both the materials are also different. That is the reason of the different resistance. So this is the equation we use to find the resistivity of a material. I hope you've understood it. Let's do the proportionality problem we were going to do. So here we have the example. Wire A has a resistance of 12 ohm. So if wire B is twice the length of A and twice the diameter, what is its resistance? Assume that both wires are at the same temperature. So I would like you to do this question before reading the answer so that you can understand it yourself. You can pause the video and do it. So if you have already done it, let me explain how we can find the answer to this question. So they're saying that wire A has a resistance of 12 ohms. So if the wire B has twice the length of wire A and twice the diameter, what will the resistance of the wire B would be? So as wire B has twice the diameter of A, it has 4 times the cross-sectional area. So because no measurements are given, we use letters to represent measurements. So as wire B has twice the diameter of A, it has 4 times the cross-sectional area. So the resistance of wire B is to be found. We are going to call this resistance RB because no measurements are given, so we use letters to represent these as well. So if length A is equal to X, the length B is equal to 2X. So the length A is the length of the wire A. This is equal to X. So the length B, the length of the wire B, is equal to 2X. This X basically represents the measurement. So if length A is X, length B is 2X because it is twice the length of the wire A. So it's going to be 2X. If area A is equal to A, then area B would be equal to 4A. So if the area is A, then the area B, if it is twice the diameter, then the area of the wire would be 4 times the area of the wire A. Why so? Because if one wire has twice the diameter of another, then it has 4 times the cross-sectional area. So this follows from the equation for the area of a circle, which is A is equal to pi into R square. So A is the area. So doubling the diameter doubles the radius. So replacing R in the equation with 2R gives new area. Pi 2R square is equal to 4 pi R square, which is equal to 4 amperes. 4A. Similarly, 3 times the diameter gives 9 times the area and so on. So area is directly proportional to the diameter square. So we're saying that area is directly proportional to the diameter square, which means that the area, if one wire has twice the diameter of another, then it has 4 times the cross-sectional area of that wire. So if length A is equal to X, then length B is equal to 2X. But if area A is equal to A, then area B is equal to 4A. So when we substitute the values, we get the resistivity of the material is equal to 12 into A upon X is equal to RB into 4A upon 2X. So R12 is the resistance of the wire A multiplying by its area and dividing by its length. And RB is the resistance of wire B, and 4A is the area of the wire B, and 2X is the length of the wire B. So rearranging and cancelling gives RB equal to 6. So the resistance of wire B is equal to 6 ohms. When we rearrange the equation and do the calculation and cancelling, then we will get RB equal to 6. So this is how we use this equation to find some complicated values as well. So remember, area is directly proportional to diameter square. Not only diameter but diameter square, which means that if a wire has twice the diameter of another, then it has 4 times the cross-sectional area. So this is how we do this calculation. Now that we've understood resistance, the resistivity of a material, the factors that the resistance depends on, like the length and area, the temperature. We have also understood Ohm's law. The current is proportional to the potential difference. There is Ohm's law, along with the resistance equation. So we are going to move ahead now on to understanding series and parallel circuits. So when we see the different lights, like the Christmas lights, they're like different small bulbs in a long wire, and they're connected to this wire, but all of these bulbs turn on when they are put into one switch. So they are connected together, not different from each other. They're connected together, so the current goes into all of these lamps. So the lamps have to get their power from the same supply. So there are 2 basic methods of connecting lamps, resistors, or any other component together. So these circuits, as you can see here, demonstrate the differences between them. So first we have the series circuit, and then we have the parallel circuit. So you can see the difference between the series circuit and the parallel circuit. Firstly, in the series circuit, these lamps are connected in series, like one after the other, like this, in the same wire, same current passage. So the lamps share the potential difference from the battery, so each glows dimly. And if one lamp is removed, the other goes out because the circuit gets broken. Okay, so this is the circuit we use in the lights I was talking about before. They are connected in series. But these lamps are connected in parallel here. So in this circuit, you can see that both the lamps are at different positions. So because they're connected in parallel, each gets the full potential difference from the battery because each is connected directly to it. So each glows brightly. And if one lamp is removed, the other keeps working because it is still part of an unbroken circuit. So you can see that the current from the battery goes over here and then comes over here and goes over here and comes over here. So if, for example, this lamp gets broken or something, it doesn't work, this lamp would still work because the circuit is not broken. This lamp has a different passage of current. So this passage of the current is still not disturbed, so the circuit is not broken, and so the electricity supply keeps flowing from here, and this lamp still glows. And because each lamp gets the full potential difference from the battery because each is connected directly to it, so each lamp glows brightly. Whereas in these lamps, because they are connected in series, they share the potential difference, and so each glows dimly. And if one lamp is removed, the other goes out because then the circuit will be broken. So this is the difference between the series and parallel circuits. So if 2 or more lamps have to be powered by one battery, as in a car lighting system, they are normally connected in parallel, so that each lamp gets the full battery potential difference. Also, so that each can be switched on and off independently. So both these lamps have their own switches here, so that if this lamp switch gets turned off, this lamp would still keep working because the electricity supply is not disturbed over here and the current is not broken here. So each of the lamps can be switched on and off independently in the parallel circuit. So here we have the resistors or any other component in series. So in this series we can see that the 18 volt is distributed equally to both of these resistors, because this resistor has a resistance of 3 ohms and this one a resistance of 6 ohms. So 12 volts is given to this one and 6 volts is given to this one. So basically the total potential difference is distributed to both of them. Whereas in a parallel resistor, if the total current in the main circuit is 18 volts, then both of the cells would get the 18 volts. The 18 volt would not be distributed in both of them. If the total current from the main circuit is 18 volt, then both of these resistors would get 18 volts of current rather than this one getting 6 volts and this one getting 12 volts. The current would be given equally to both of them, which is equal to the total current coming in the main circuit. So these are the cells connected in series, and the total potential difference across them is the sum of the individual potential differences. So 18 volts is distributed equally to each of these cells. So each of these cells gets 1.5 volts. So here a mistake has occurred. One of the cells is the wrong way around, so it cancels out two of the others. So you can see that because one cell got wrong, all of the other cells would shut down automatically because the circuit would be broken. As you can see, the cells are connected in series, so the total potential difference across them is the sum of the individual potential differences. So the potential difference given is 4.5 volt, and this is distributed equally to all of the cells. So each cell gets 1.5 volts here. Whereas in the parallel cell, the potential difference across parallel cells is only the same as from one cell, but together the cells can deliver a higher current. So the potential difference is 1.5 volt, then each of the cell would get 1.5 volts. So the potential difference across parallel cells is only the same as from one cell, which is 1.5 volts. It is the same as for one cell, but together all of these cells with 1.5 volts can deliver a higher current. So you can see that parallel system is better than a series system because it needs less potential difference and they can convert that potential difference into a higher current. Whereas in a series, the potential difference gets distributed into each of the cells. Well, both of these, like the series and parallel circuits, are used in different scenarios in different places. The series is also an important circuit, and the parallel is also an important circuit. So, if two or more resistors are connected in series, they give a higher resistance than any of the resistor by itself. If two or more resistors are connected in series, they give a higher resistance than any of the resistors by itself. So the effect is the same as joining several lengths of resistance wire to form a longer length. So if resistors R1 and R2 are in series, their combined resistance is R, given by this equation. We just plus R1 into R2 and we get R. But if two or more resistors are connected in parallel, they give a lower resistance than any of the resistors by itself. Then the effect is the same as using a thick piece of wire instead of a thin one. So there is a wider conducting path than before. So if resistors R and 2 are in parallel, their combined resistance is given by this equation. 1 divided by R1 plus 1 divided by R2 and B is equal to 1 divided by R. For 3 or more resistors, the equation can be extended by adding I divided by R3 and so on. So if the equation is rearranged, it becomes something like this. Remember, this method of calculation works only for two resistors in parallel. Combined resistance is equal to resistance multiplied divided by resistances added. So here we have the first example. In this, they're asking us to calculate the potential differences across the 3 ohm resistor and the 6 ohm resistor here in this circuit. So the first stage is to calculate the total resistance in the circuit and then use this information to find the current. So the total resistance would be 3 plus 6 ohms, which is 9 ohms. So the total resistance is 9 ohms. We just add up the resistor's values and we get the total resistance. So current is equal to potential difference upon resistance. So we divide 18 volts, which is the potential difference supplied, with 9 ohms. When we do so, we get 2 amperes. So the current is 2 amperes. Knowing that the 3 ohm resistor has a current of 2 amperes in it, we can calculate the potential difference across it. Then potential difference is equal to current into resistance, which is, we know the current, so it's 2 amperes multiplied by 3 ohms. We are going to take out the potential difference of the first resistor and then the second resistor. So 2 multiplied by 3 is 6 volts. So the potential difference across the 3 ohm resistor is 6. The potential difference across the 6 ohm resistor can be worked out in the same way. However, it can also be deduced from the fact that potential differences across the two resistors must add up to 18 volts, about the potential difference across the battery. So by either method, the potential difference across the 6 ohm resistor is 12 volts, because of course if we add 6 into 12, then we get 18. So if we know that this resistor has the potential difference of 6 volts, then the sum of both of these resistors would add up to 18 volts, which means that 6 ohm resistor has a potential difference of 12 volts. But we can also use the equation to find this out, or this fact that they must add up to the 18 volts. And either way, we have to take out the first resistor's potential difference using this equation. So this is how we found the potential differences across both of these resistors. Firstly, what we did was we calculated the total resistance in the circuit, which was 9. Then, to find the current in the circuit, we divided potential difference by resistance. So we do know that the potential difference is equal to 18 volts, like this is the total potential difference. It gets distributed into these, so we have to find out the potential difference of each of these. So we first find out the current which is in this circuit. So we divide the potential difference by the resistance, the total resistance, both of these, which is 9 ohms. When we do so, we get 2 amperes. So now we have the current as well as the resistance and the potential difference. So now that we know that 3 ohm resistor has a current of 2 amperes in it, we can calculate the potential difference across it. We use this equation, and that is how we got the 6 volts. We use the same equation for this ohm resistor. The resistance would be changed to 6 ohms, and when we do so, when we multiply 2 by 6, we'll get 12, of course. And so this is how we get the, remember that the answer, when we add up both of the potential differences, should add up to the potential difference 18 volts, which is across the battery. So this is how we can calculate potential differences across different resistors. These were only 2 resistors. In the same way, we can have 3 resistors or 4 resistors. So this is how we measure it. Now, this was a simple question. Let's do another question here. So, here we have 2 resistors parallel in a parallel circuit. See, before they were in series, right here they are in parallel. So they're asking us to calculate the currents I, I1 and I2 in the circuit. So this also depends on the resistance of this resistor. Now, let's see. The 3 ohm resistor has the full battery potential difference of 18 volts across it. So I is equal to potential difference upon resistance. Okay. So this is equal to 18 volts upon 3, which we get is 6 amperes. So we found the current of this resistor, 6 amperes. We write it down here. Using the same method, we can find out I2 is equal to 3 amperes. The current in I is the total of the currents in the 2 branches. So I is equal to I1 plus I2, which is equal to 6 amperes plus 3 amperes equal to 9 amperes. So this is how we can calculate the currents across different resistors.
So now we're going to look at what diodes are. We have read them before. They are also a resistance component. which allow current to flow in one direction only. So the circuits here show what happens when a diode is connected into a circuit one way round than the other. So here we have the forward biased diode. So when the diode is forward biased, it has an extremely low resistance. So a current flows in it and the lamp lights up. So in this case, the arrowhead points the same way as the conventional current direction, which is from positive to negative, right? But if the diode is reverse biased, like this, it has an extremely high resistance and the lamp does not light. In effect, the diode blocks the current. So this diode is forward bias, which means it has an extremely low resistance in this direction. But when it is reverse bias, it has a high resistance, extremely high resistance, and stops the current from flowing. So, rectification is the process of changing alternating current to direct current. Alternating current is A dot C dot and direct current is D dot C dot. Alternating current is basically when current moves backwards and forwards. That is called an alternating current. Whereas direct current it just moves forwards smoothly, like in a battery. So we can use diodes as rectifiers to change alternating current to direct current. So it is done using diodes which doing this job are known as rectifiers. So this is a simple rectifier circuit. The diode lets the forward part of the alternating current through but blocks the backwards part. So the current in the resistor flows one way only. It has become a rather jerky form of direct current. Alternating current is kind of like it just moves forwards and then goes backwards, and then moves forwards and then go backwards a little, something like this. So what a diode does is that it lets the forward parts through, it lets it pass forward but blocks the backwards part. So the current flows in one way only, but it stops at different points, the points in which it's supposed to move backwards. So when it stops there, it becomes a little jerky. So it moves forwards and then it stops, and then it moves forward and then it stops. So an oscilloscope can be used to show how the circuit changes the alternating current input. The bottom part of the output waveform is missing. This is the part where it moves backwards. So the current is flowing one way in surges with short periods of no current between. But this can be solved with extra components added to the circuit. The pulsing current from a rectifier can be smoothed out. So then we have a steady direct current output. So this is how we use diodes as rectifiers to change alternating current to direct current, and how the diode can be reverse biased and forward biased to have an extremely high resistance at one point than the other. So I hope this was clear. So this was a component in circuits. Now we're going to look at another component, which are the LEDs. So right now we're looking at different components of circuits, like the LEDs, diodes. Next we're going to look at the potential divider and the reed switch. So they're going to be very interesting, and I'm going to just give some brief information about each of them. So LEDs. LED stands for light emitting diode. And as its name suggests, it is a diode that gives off light when a current is passed through it. Now we may have heard the term LED. We have heard it like LED TVs, something like that. So LED is basically light emitting diode. It gives off light when a current is passed through it. So red, green and blue LEDs are used as indicator lights on electronic equipment. You may have seen it in a remote control. When we are controlling the remote, there is a small red light coming out from one end of the remote. This is an LED. It is an indicator light. And in many electronic equipment, this light is used as an indicator that something is being charged or something is working right now. It is turned on. So arrays of white LEDs are the source of light in some low energy bulbs and torches. So white LEDs are used in low energy bulbs and torches. Like in torches, we have seen some LEDs. They are called LED torches. So this is the circuit symbol for LEDs. It's a diode, but with some arrows in the opposite direction from the diode, like this. So this shows that it's a light emitting diode. Next, we have a potential divider. So a potential divider is an arrangement that delivers only a proportion of the voltage from a battery. So here we have the circuits A and B which show this principle. So this is the circuit A and this is the circuit B. In circuit B, you can see we have a variable resistor like this, and there is a small resistor here, a simple resistor. Here we have the battery. So using a variable resistor, the output voltage can be changed. This is the output voltage. Here it can range from 0 to 3 volts depending on the settings on the variable resistor. So this is basically a potential divider. It delivers only a proportion of the voltage from this battery. And this voltage, this proportion of the voltage can be changed. Like it can go to 2 volts, we can change it to 3 volts or 1 volt depending on the setting on the variable resistor. In this potential divider, the lower resistor has half the total resistance of the 2 resistors. So its share of the battery's voltage is also half. So the output voltage is also a proportion of the voltage from the battery. So this is a potential divider. It's an arrangement that delivers only a proportion of the voltage from a battery. This voltage can be changed, which is by using a variable resistor, or kept like this. Some electronic circuits are designed to switch on when a voltage reaches a set value. So if the variable resistor in circuit B was replaced by an LDR, then the circuit controlling a lamp could be switched on when it got dark. Similarly, a fire alarm could be switched on by a potential divider containing a thermistor. So these are the different ways the potential divider can be used. So this was the potential divider. Now we're going to look at the reed switch, another component of the circuit.
This is a reed switch. So this reed switch is operated by a magnetic field. So in this example, the contacts close. These are the contacts. They only close if a magnet is brought near, then open again if it is moved away. So burglar alarm circuits often contain reed switches. The magnet in that case are attached to the moving parts of windows and doors. So if anybody opens a window or the door, the magnet moves towards the reed switches, and the reed switch, because of that magnetic field, the contacts of the reed switch close. So the circuit becomes complete and the burglar alarm turns on. So here we have a cutaway form of the reed switch. The reed switch is made up of leads which are in a glass capsule. With a coil around it, a reed switch becomes a reed delay. So the current in one circuit through the coil switches on another circuit through the contacts. So this is how a reed switch can be made a reed delay. The current in one circuit switches on another circuit. So that is a reed delay. So these are some brief definitions of the reed switch, the LDR, the potential divider. I hope you're getting it all. They're pretty simple. So now, after reed switch, we're going to move ahead on to understanding electrical energy and power. So power is the rate at which energy is transferred from one store to another. So the SI unit of power is the watt, which is represented by a capital W. So this is the equation we use to measure power, to calculate power. Power is equal to energy transferred upon time taken. Dividing energy transferred by time taken, we get power. So here you can see a circuit. In this circuit, the battery is supplying 5 joules of energy per second. So the power it transfers is 5 watts. The lamp is transferring power to its surroundings at the same rate, 5 watts. So appliances such as toasters, irons and TVs have a power rating marked on them, either in watts or in kilowatts. 1 kilowatt is equal to 1000 watts. For circuits, there is a more useful version of the power equation. If a battery, lamp, or other component has a potential difference across it and a current in it, the power is given by this equation. Power plus potential difference multiply by current. So we can rearrange this equation to get different values. So this is the power equation for circuits. Now let's look at how we're going to calculate electrical energy. So if the power of an appliance is known, the energy transferred in any given time can be calculated like this. So energy transferred is equal to potential difference multiplied by current multiplied by time taken. In symbols we get E is equal to VIT. So this is the equation we use to find energy transferred, the electrical energy. So if the power of an appliance is known, the energy transferred in any given time can be calculated using this equation, which is energy transferred is equal to power into time taken. You can also write it as like this. Energy transferred is equal to potential difference into current into time taken is equal to. So this is potential difference into current basically is the equation for power. Power is equal to potential difference into current. So then when we multiply both the values, we multiply it with time taken, we get the energy transferred. In symbols, we write it as E is equal to VIT. So for example, if a 1000-watt heating element is switched on for 5 seconds, energy transferred is equal to 1000 watts multiplying by 5 seconds, which is 5000 joules. So the heating elements gives off 5000 joules of thermal energy. In the same way, if a 12-volt heater takes a current of 2 amperes, if it is switched on for 60 seconds, how much energy is transferred to the thermal energy? Now I want you guys to find the answer of this question using this equation. Pause the video and write it down. If you have done the answer, let me explain how we do it. So energy transferred is equal to potential difference into current into time. Like this, right? We have given the potential difference, which is 12 volt, the current, which is 2 amperes. So when we multiply them and the time taken, which is 60 seconds. So when we multiply all the values, we get 1440 joules of energy. So all of this energy is transferred to thermal energy. So energy transferred to thermal energy is equal to 1440 joules. I hope your answer is the same if you've done the calculation correct. So this is how we calculate electrical energy. How we calculate power, this is the equation we use for power. There is also an equation of power, energy transferred is equal to time taken. But if we don't have the energy, we can find power with potential difference and current. Then we can find electrical energy transferred by power into time taken also by this equation. This is the same as power into time taken, we're just breaking down the power here as well. So now that we've understood electrical energy, it was very simple as you saw, and the equations are just supposed to be remembered. That is how we are going to understand whenever we're given a question. We can predict which equation is going to be used in that scenario, and it all depends what we are given, what values are we given. If we are given the power and time taken and they're asking us to find the energy transferred, we use this equation to do it. It's pretty simple, right? We just have to memorize these equations. If we are given the potential difference in current and they want us to find out the power, or if we have to find out the power to find another answer, which is not actually the power, something else, but we have to find the power in order to get it, we use the equation. So we use different and multiple equations to find a single answer. And it all depends on the question, what the question is handing over, what are the values given, and how we are going to use those values to find another value to find the answer of the question. So now we're going to move ahead on to how we live with electricity. So living with electricity. So when you plug a kettle into a main socket, you are connecting it into a circuit. The power in that circuit comes from a generator in a power station. The supply voltage depends on the country. So for household circuits, some countries use a voltage in the range of 220 to 240 volt and others in the range 110 to 130 volts. So Mains current is the supply voltage basically. This is the supply voltage, the mains current. Mains current is alternating current. So this means that it flows backwards and forwards, and so on 50 times per second in some countries. So the mains frequency is 50 Hz. In other countries, the mains frequency is 60 Hz. So alternating current is easier to generate than one-way direct current, like that from a battery. So this is another piece of information. The more oscillations it does, like backwards and forwards movement, are basically oscillations. So it does this 50 times per second. So we say that the mains frequency is 50 Hz. In other countries, the mains frequency is 60 Hz. So alternating current is easier to generate than one-way direct current, like that from a battery. So this is the mains current. Voltage range from 220 to 240 volts, and in some other countries it ranges from 110 to 130 volts. Now here we have the main wire. We use the main electricity, the mains current, from the plug. So the current supply is coming from switches and switchboards we have in our houses. We put a plug and the energy gets transferred to the element or the device we are wanting to start. So the wires, all of the devices like the kettle or any other electronic device has a cable, a plug as well. In this cable we have many other wires, and these wires are something like this. We have three different wires: the live wire, the neutral wire, and the earth wire. So the electric kettle has a heating element below it. We have the cable which comes from this heating element and goes into the switchboard. So when we turn on the switch, the circuit completes and the current starts to move into the heating element. Now we have three different wires in a cable. So altogether these wires form a cable which we use to turn the heating element on. So first we have the live wire. This is red in color. If it is harmonized, it gets something like this, like a brownish color. It's brown color. So mostly it's red in color. So the live wire, this goes alternately negative and positive, making the current flow backwards and forwards in the circuit. That is how an electric and alternating current is produced. So this wire goes negative and positive alternately. So the current flows backwards and forwards in the circuit. Then we have the neutral wire, which is black in color, and if it is harmonized, it becomes blue in color. This completes the circuit. So in many systems, it is kept at 0 voltage by the electricity supply company. So neutral wire's use is just to complete the circuit, and it is just kept at 0 voltage because it's just neutral. It is used to complete the circuit simply. Then we have the switch. This is fitted in the live wire. It would work equally well in the neutral, but wire in the cable would still be live with the switch off. So this would be dangerous if, for example, the cable was accidentally cut. So that is why we keep a neutral wire. So if we fit the switch in the neutral wire, the cable would still be live with the switch off. So this can be dangerous if the cable was accidentally cut. You don't want to be electrocuted, right? So the switch is fitted in the live wire. Then we have the fuse. This is a thin piece of wire which overheats and melts if the current is too high. When it melts, it just blasts a little, gives a little blast, and just the switch gets over, like it stops working. That's the fuse. When we say that the bulb fused, this is what happens. If the current is too much in the bulb, then this thin piece of wire overheats and melts. This happens if the current is too high, higher than the actual need of the bulb. So then it basically fuses the bulb. It doesn't work anymore. So like the switch, it is placed in the live wire, often as a cartridge. If a fault develops and the current gets too high, the fuse blows and breaks the circuit before the cable can overheat and catch fire. So a fuse is used for security. If the current gets too high, it just blows and breaks the circuit before the cable can overheat and catch fire. So many circuits use a circuit breaker instead of a fuse. This is a strip switch. It's also called a fuse box. It's kind of like a switch. If it overheats, the switch turns off. It gets stripped. So this was the fuse. Lastly, we have the earth wire. This is the grounded wire. This is a safety wire. It connects the metal body of the kettle to the earth and stops it becoming live. For example, if the live wire comes loose and touches the metal body, a current immediately flows to earth and blows the fuse. So this means that the kettle is safe to touch. Just to keep us from electrocution, in simple words, the earth wire is a safety wire. It connects the metal body of the kettle to the earth and stops it becoming live. So if the live wire becomes loose and touches the metal body, the current immediately flows to earth and blows the fuse. So these were the cable, what is inside the cable. Then we have double insulation. Some appliances, radios for example, do not have an earth wire. This is because their outer case is made of plastic rather than metal. So the plastic acts as an extra layer of insulation around the wires. So this is double insulation. The plastic is a good insulator, like some table lamps have an insulating body and do not need an earth wire. So for extra safety, circuits may be fitted with a type of breaker called a residual current device, RCD. This compares the currents in the live and neutral wires. So if they are not the same, then current must be flowing to earth, perhaps through someone touching an exposed wire. So the RCD senses the difference and switches off the current before any harm can be done. So this is what double insulation and residual current devices. These are basically just for safety and to prevent electrocution. So now we're going to move ahead on to what plugs are. So plugs are a safe and simple way of connecting appliances to the mains. Over a dozen different types of plugs are in use around the world. A few countries use a 3-pin plug with a fuse inside. So the fuse value is typically either 3 amperes or 13 amperes. You probably have seen these, like the big ones which have 3. So they're like a big 3-pin plug. They have 3 pins. That's it. They are mostly for big appliances like a big microwave, like an oven or a fridge. So we use 3-pin plugs for big devices most of the time. So we use a 3-pin plug which has a fuse inside. The fuse value is typically either 3 amperes or 13 amperes. So this tells you the normal current in the appliance, but as close to it as possible so that the fuse will blow as soon as the current gets too high. So if a kettle takes a current of 10 amperes, then a 13 ampere fuse is needed. If a TV takes a current of 0.2 amperes, then a 3 ampere fuse is needed. The TV would still work with a 13 ampere fuse, but if a fault developed, its circuits might overheat and catch fire. So that is why the fuse value is as close to the current as possible, so that the fuse will blow as soon as the current gets too high. 3 amperes, like from 0.2, if it reaches to 3 amperes, the fuse will trip off. The fuse will blow. So there is less risk. If it's a 13 amperes fuse, an appliance would still work, but still there's a much bigger risk because it's a big difference. So till it reaches to 3 amperes, the circuits might overheat and catch fire. So that is why we use a fuse value which is as close to the current as possible. So these were plugs. Now the last topic of this chapter are the electrical hazards. So mains electricity can be dangerous. So here are some of the hazards. So first, old frayed wiring. This is a hazard. Broken strands mean that a wire will have a higher resistance at one point. So when a current flows in it, the heating effect may be enough to melt the insulation and cause the fire. This is a hazard, old frayed wiring. Then we have long extension leads. So long extension leads. These may overheat if used when coiled up. So the current warms the wire, but the heat has less area to escape from a tight bundle. So that is why we keep the wires long and open so that even if the current warms the wire, the heat has area to escape. But with a tight bundle, it has less area to escape. We might need long extension leads. There are many different reasons why we need long extension leads. For example, if we have a main switch far off in a different corner and we are sitting in a different corner, we would need long extension leads. But of course, in those cases, we won't put them into a tight bundle because we want them to get loose and reach the position where we are sitting. But if we have long extension leads and we are close to the main circuit, then we might tie them up into a tight bundle, which can be a hazard. Then we have water in sockets or plugs. Water will conduct a current. So if electrical equipment gets wet, there is a risk that someone might be electrocuted. We have always been told never get our devices wet. Never put wet hands on devices because water can conduct a current, especially in sockets or plugs that can be extremely dangerous. Lastly, we have accidentally cutting cables. So with lawn mowers and hedge trimmers, a plug-in RCD can be used to avoid the risk of electrocution. The RCD, again, what we just read before, the residual current device, this compares the currents in the live wire and neutral wire. So if they're not the same, then there's a chance that the current must be flowing to earth. So plug-in RCD can be used to avoid the risk of electrocution with lawn mowers and hedge trimmers because they might accidentally cut the cable themselves. So one tip of advice. So one point to remember, if an accident happens and someone is electrocuted, you must switch off at the socket and pull out the plug before giving any help so that the current stops flowing, the circuit gets broken. So this was all for today's chapter. It was, as you saw, a very big chapter, right? This was our 8th chapter, electricity. In this chapter, we read static electricity, the electric charges, charging and discharging, positive and negative charges, electrostatic charge, attraction and repulsion between charges. We read how friction causes charging and charging by induction. Then we understood conductors and insulators and semiconductors as well. We understood the unit of charge, what the unit of charge is, this is the coulomb, how we use electrostatic charge in different devices like the electrostatic precipitator, the photocopier, and the laser printers in the same way as a photocopier. We understood electric fields, the electric field patterns, ions, what ions are. Then we understood the simple circuit, the different circuit symbols, how we can measure current, the link in between the charge and current direction and electron direction, the difference between that. We understood potential difference, then voltage across a cell. Then we understood resistance, the equation we use to measure resistance and the unit of resistance. We understood all of the resistance components. We also did some questions related to resistance. We understood Ohm's law, the current proportional to the potential difference. Then we understood how resistance depends on length and area. So we did some proportionality problems as well here. And then we understood series and parallel circuits. We did some questions related to series and parallel circuits and the combined resistance. And then we understood diodes. We understood some like the components, electric components like the diodes, how we use diodes as a rectifier, LEDs, what they are. I hope you remember all of these, and if you don't, you better watch it again. The potential divider, the reed switch, and then we understood electrical energy and power, the equation for power and energy transferred, and the many different equations to like the power equation. Lastly, we understood how we live with electricity. We understood the mains current, the different wires in a cable, like the live wire, the neutral wire, the switch, the earth wire. We understood double insulation. Then we understood the plugs, 3-pin plugs. The plugs also have fuse in it. And last but not the least, we understood electrical hazards. So this was all for today's chapter, electricity. So it was a very easy chapter, even though it was very complicated and a lot of stuff was in it to understand. We have successfully completed the 8th chapter of our physics O-level lessons, electricity. Now the next chapter is going to be magnetism. So thanks for watching this video. I hope you've understood everything, and I hope you will memorize all of the equations and the definitions I wrote in this chapter. So I'll see you in the next video.